Hey pre-calc students, this is Unit 8, Day 6. Today we're going to be talking about extending de Moivre's theorem a little bit further to find what's called the nth root of polar numbers. So today what we're going to do when we find the nth root of polar numbers is we're going to focus on something called the principal root. And I'll explain what that means when we get into some examples, but the principal root of a number is something that we'll be finding by applying an application of de Moivre's theorem today. And if you're like, wait, hang on, what's de Moivre's theorem again? Well, it was yesterday's lesson, but we can recap it quick. De Moivre's theorem says that we can raise polar numbers to a power. So it's r cis theta to the n, but that would be equivalent to doing r to the n cis theta times n. So if we can remember that that's what de Moivre's theorem states, what I want to know is like, well, what about the square root of a polar number? Right, so when we say that we're taking roots of polar numbers, we'll start with our famous friend, the square root. So the square root of r cis theta, the nice thing is that we have a way to express the square root as an exponent. And what sometimes students incorrectly say is that it's the same thing as this squared. And I understand why they say it, because squaring it would get rid of the radical. But remember that radical r cis theta would be the same thing as r cis theta raised to the 1/2 power. So that fractional exponent is equivalent to taking the square root. And the second I write that, then I can actually translate this using de Moivre's theorem to r would get raised to the 1/2 power, and the angle theta on the inside would get multiplied by a half, so it would be half of theta. You may also see that written as, instead of r to the 1/2, maybe translating that back to a radical, so radical r. And instead of seeing half of theta, you might just see that written as theta divided by 2. Both of these are equivalent, right? It would be the same thing. So whichever way you kind of like better, or maybe a combination of the two, that would be fine to write that way. Extending this a little bit further, what if I said, let's still see what the cube root of a polar number would look like, the cube root of r cis theta. Well, the cube root of r cis theta, same idea, just take r cis theta and then raise that to the 1/3 power. Convert it to that fractional exponent. So the two ways that we can write our final answer here would be by saying that it's r to the 1/3, and then theta would get multiplied by 1/3 on the inside. Or again, if you don't like that look, you could equivalently rewrite it as the cube root of r, and that theta is getting divided by 3. So what we're building towards here is I don't always have to be taking the square roots or the cube root of a number. We can be taking any root in general. So when we take the nth root of a number in r cis theta form, that's what we said at the top, finding the nth root of polar numbers. You can always translate this over to that fractional exponent, right? To the 1/n powers, what that would be raised to. But the result of that is that I would just take r to the 1/n power, and then theta would get multiplied by 1/n like this. Or again, the other way is just by doing the nth root of r, and then theta would get divided by whatever n is. So whichever form you kind of like the best, these are equivalent forms. This is just another application of de Moivre's theorem as it relates to roots. And roots will actually be a pretty important part of what we do moving forward, because when we take the root of a number, it may have a connection to, in the next few days, solving some equations. And that's what we're building towards by learning this process. So if we take a look at some examples, let's start with something that's already in a nice polar form for us. So for example, the fifth root of 32 cis 150. So to do the fifth root of 32 cis 150, the first thing I would do is apply that rule. And if you want, you can just rewrite it as this to the 1/5 power. Up to you if you want to continue to do that step. But what that means is that I'm going to do 32 to the 1/5 power. And then 150 is going to get multiplied by a fifth. 32 to the 1/5 power, or the fifth root of 32, is 2. That's a nice value there. And then 150 divided by 5, or 150 times the fifth, is 30. And of course, the last step is, if this is a nice angle for now, we'll work on converting that back into rectangular form. So 2 cis 30, maybe off to the side here, we draw a really quick picture. 30 is the reference, 2 is the hypotenuse. The legs would be 1, and then this would be radical 3. So the fifth root of 32 cis 150 that we started with equates in rectangular form to radical 3 plus I, and that would be the final answer. So if you're good with Demoivre's theorem from yesterday, I don't think we'll have too much trouble using this root idea today. Okay, so let's actually try another example then. So if we take a look at something like the fourth root of negative 16. Okay. Fourth root of negative 16 is kind of an interesting case because if you look at just the fourth root of positive 16 to start, the fourth root of 16 is 2. Because 2 times 2 times 2 times 2 is 16. So then some might beg the question, like, is the fourth root of negative 16 equal to 2i, maybe? I don't know. Can we take the fourth, because we know the square root of negative 1 is I, so is the fourth root of negative 1 still I? I'm not sure, but we'll be able to confirm that in a minute by going through our process here. First thing we have to do is take the negative 16 and convert. Let's put this in r cis theta form so we can apply the root rule now using Demoivre's theorem here. Well, negative 16 is just 16 to the left, isn't it? So this would be the fourth root of 16 cis. The angle would be 180. Draw a picture if you need it for that. But that would turn into 16 cis 180. Well, if I now apply the rule, it would be the fourth root of 16, which I already told you what that was, cis, and then 180 is going to get multiplied by a fourth, or you can divide by 4. That would be fine too. Which turns into 2 cis 45. So is 2 cis 45 the same as 2i? It's not looking like it, but let's draw the picture just to make sure. If I draw the triangle, here's the angle of 45 degrees. 2 is on the hypotenuse. This is that weird pattern where there's no radical 2 here, so that means there's radical 2 on the legs. And the number out front would be 1 radical 2 each. So this would become radical 2 plus I radical 2, which is definitely not 2i. So I'm going to go back up here and say, like, I thought it was 2i, maybe, but it turns out that it's not after going through all the process here. So the fourth root of these negative numbers, they are complex, but it's not the complex number that we might have predicted it was using what we know about square roots of negatives. So a little bit of a twist to that, but here's the final answer, radical 2 plus I radical 2. Okay, a little bit more practice here. Let's try the cube root of 8i. Cube root of 8i. So for the cube root of 8i, the way we're going to start is, again, I can't just say this is the cube root of 8 is 2 and the cube root of I is question mark. I'm not really sure. You have to convert this first. So we'll go ahead and start by converting. Once I have it converted, then we'll go ahead and take the cube root. 8i would be up 8 units, right? And the angle there would be 90. So this becomes the cube root of 8 cis 90. And now we can apply Demoivre's theorem. So this would become the cube root of 8, or 8 to the 1/3 power, whichever you want. You know, in terms of using your calculator, it's up to you if you need it for something like this. 90 is going to get divided by 3 or multiplied by 1/3. This turns into 2 cis 30. I think we did that one earlier. Should I cheat? Let's say 2 cis 30. Oh, not on that page. Yeah, we did 2 cis 30 earlier. 2 cis 30 is right here, radical 3 plus I. So I don't need to probably redraw the whole picture for you here. It's just really getting practice with this new rule here today that this would become radical 3 plus I. Okay. So maybe we'll do just one more example just to give you an idea and get used to the process. Let's talk about the fourth root of 81. Now, the fourth root of 81, when it's a positive on the inside, it's a little bit more direct. You might even know what the answer is here. But let's do the whole converting process and just make sure we've got the process down here. So 81 is the same thing as 81 cis 0. And given the options between 0 and 360, right? Think about the picture, it's 81 to the right. Let's choose the smaller angle, because when I divide this by 4, it's probably going to be a really nice number. It's still going to stay 0, right? It's the fourth root of 81 cis, and then it turns into 0 divided by 4, which is still 0. Well, the fourth root of 81, we still have to know what that is. And the fourth root of 81, whether you do it on the calc or not, is 3. And 0 divided by 4 is 0. So what's 3 cis 0? Imagine this was the length of 3 up here. 3 cis 0 is just 3, or 3 plus 0i. And the last thing I want to mention is that this is called the principal roots. So I mentioned that term at the beginning of the notes today, and I said I would explain what that means. The principal root is sort of the first answer that you get when you take the fourth root of 81. But what we're going to learn in the next lesson after this is that there are 4 fourth roots of 81, which is pretty amazing because we're used to, I would say, just taking a root and getting a single answer like we did for all the others. But there are 4 fourth roots of 81 because it really comes as a result of solving something that looks like this. If I started you with this equation right here, and then I had you add the 81 to the other side, and then take the fourth root of both sides, wouldn't it turn into the problem that we're solving right here? The answer is yes, but we know from earlier on in our course that this has 4 solutions. So we're going to talk about how we can actually take our first principal solution, the first solution you get, and then we'll use that to get the other 3 answers and be able to solve this completely. So that's kind of where we're headed with all this, but as long as you got the process down for taking roots, that is all for today. So let me know if you have any questions. Have a great rest of your day.